Hello everybody. So this week's lecture is on linear systems, or systems of linear equations. Like, it's a little wordy, so we like to just call it linear systems. And I think the two techniques of solving them, using the substitution method or the elimination method, are pretty straightforward and pretty easy to understand. The hard part about this particular chapter is our favorite of all time, word problems. So in this video, I'm going to go through some examples of different types of word problems that might be similar or sort of similar, or something that to help us set up these equations so that we can actually solve them for this week. So that's what this video is all about. It's going to be word problems. What up, word? So here's an example of one of the types of word problems that we might come across. It says a spring play was attended by 429 people. Admission was $8 for each adult and $4.50 for each child. The total receipts were $2,641. How many adults and how many children attended? Now, whenever we do word problems, the first thing I like to do is I like to identify my variables and assign them values so that I know which letter is representing which unknown. Because this is the entire chapter on linear equations, there's going to be two equations with two unknowns. So I have to keep that in mind as well. So what are my unknowns? Well, what am I trying to find? The first thing I go to is the question, how many adults and how many children attended? So I need to know the number of adults and the number of kids that attended this play. So I like just to say, okay, so let A equal the number of adults that attended. And then I go through and do the exact same thing. Oh, children, I think we'll call that C. So let C equal the number of children that attended. Now I know what my variables represent. It's the number of people that are called either adults or children. Okay, so then I go into my equation. I say, what information do I know? And it says up here, it was attended by 429 people. Well, what do those people make up? Well, those people are a combination of adults and children. Well, I don't know how many adults and I don't know how many children, but it would be adding those two together. So my first equation would be the number of adults plus the number of children would have to equal the total number of people, which is 429. Okay, so that was the first sentence, and that gave me my first equation. Now I need to once again reiterate that this is a linear system. So I'm going to have two equations with two variables, the same variables, but two different equations. So now I kind of have to think, okay, one equation's done. What else can I come up with? And we look and say, what other values are given to us? Oh, we're told that it's $8 for each adult and $4.50 for each child. Okay, well, let me think. If I had 3 adults, what would the value of my tickets be? 24, because I would take 8 times 3. Oh, so to find the value of adults, I would take 8 times the number of adults. That would give me the total value of money that I received from adults. Well, I don't know how many adults. That's my variable A. So I once again will use that. So all the money that I got from adults could be represented by 8A. $8 times the number of tickets that we sold. Similarly, it was $4.50 for each child. The total number of money that I get from the children would be $4.50 times the number of children, which once again we don't know. That's our letter C, but we can still write that as a multiplication. So it's plus 450 times C. And that's going to equal, well, let's see, this is the amount of money that we got from the adults, the amount of money from the children. We add it together would give us the total amount. So this is going to equal the 2641. Now we have the system set up that we can solve this either by the substitution or the elimination method. I like the elimination method myself. And I don't really like multiplying through by decimals, so I'm going to get rid of my a's by multiplying this top equation by -8. Remember, it has to be an opposite so that it'll cancel out. I'll just rewrite that underneath. -8 times a is a -8a. -8 times c would be a -8c. And -8 times that ends up being -3432. Now I have these two equations that I can add. 8a minus 8a cancels out it better. That's why I multiplied by that -8 is to eliminate the a's. I have a positive 4.5 and I'm taking away 8. Remember to line up those decimal points there, one of each, so we're subtracting. That ends up being a -3.5c. Remember, there's zeros here. You would have to borrow to take 5 from the 0. This is my subtraction set up backwards. Equals, and putting those together is going to give us a -791. Once again, there's one of each sign, so you subtract and keep the sign of the larger, which is the 3000 number. And now to get c by itself, we're going to have to divide by the -3.5, because a negative divided by a negative is a positive. And here's your moment of truth. When you get out your nice little handy dandy, you should get a pretty number. Because let's face it, we can't have part of a kid. So 791 divided by 3.5 ends up being 226. So you have 226 children tickets, or children attended. Now make sure we answer the question. It asks not only how many children, but how many adults. How do we find that out? Well, I would go back into that first equation. Adult tickets plus children tickets has to equal 429. So I don't know the adult tickets, but I now know that the children tickets are 226. So now we subtract both sides by the 226 to find out that A is going to equal 203 adults. These are all word problems. These numbers mean something. You better label them. And that's how we would set up something about giving us a total. Now notice the types of problem. We needed to know the adults and the children, and so one of our equations was simply add the variables and equal some sort of total. Oftentimes we have word problems like this, and that's what one of your equations is going to be, is just your two variables added together equal to some sort of total. That's not always, but most of them have that type of situation. And then there's a value that's assigned to each of your variables, and you multiply the variable by that value that it's assigned to, and that's going to give you some other type of total. Once you have the equations, the system set up, you can solve by either substitution or elimination. Some of the problems have solutions to them, or they have some sort of percent added in to our system. So in this one it says solution A is 50% acid and solution B is 80% acid. How many liters of each should be used in order to make 100 liters of a solution that is 68% acid? So essentially we need to mix the two. The 50 is too weak, the 80 is too strong. So we need to make some sort of combination to get 68%. Now it's not just a 50-50 split here. We need to find out exactly how many liters of each kind. All right, so once again, the first thing I always do is I identify my variables. What am I trying to solve for and what am I going to call those? So I go to my question, how many liters of each? Of each what? Of each solution. So I'm going to say let A equal, now it's how much of something. We're talking about liters. So let A equal the liters of solution A. And since my other one is B, we'll say let B equal the number of liters of solution B. All right, now what do we know? We have these percents. Slow it down. How many liters total am I going to have? How much am I mixing? Where does it tell me that? Oh, I'm going to be making 100 liters. So I'm only going to have a total of 100 liters between the A and the B. Okay, so once again, that's one of my equations. A plus B is equal to 100. Okay, that's good. Now, what else do I have? Oh, I have percents of stuff. Okay, so we're going to do the same type of thing as we did in the last problem, is you multiply that percent times the number of liters. That's going to let you know how much. And the great thing is here, we don't have to convert the percent into a decimal because we're just going to use the percent all the way across the board, and that consistency will keep it with the percents. So take the 50 times the number of liters to find out how much of that solution would be of that 50%. And we add to that the 80% times the number of liters here, which we don't know, so we call that B. So we took percent times liters plus percent times liters is equal to percent times liters. Has to be consistent all the way through. We can add these two together because it's a percent times liter and a percent times liter. When you add two things that have that same label, their total is going to be the same, percent times liters. Now that we have the equation set up, we can go through and solve. You probably want to clean up that 68 times 100. That's just 6,800. And I would want to get rid of A's, I think, because they're a little bit smaller. I don't want to multiply by big numbers, so I'm going to take this equation to cancel out with this A. I need another 50, but it needs to be a negative so that they cancel. I need one to be positive, one to be negative, so I multiply that entire equation by a negative 50. I'm going to rewrite that underneath. So we have negative 50A minus a 50B is equal to negative 5,000. Remember, whatever you do to one side of the equal sign, you have to do to the other. So you have to make sure that you multiply the right side of the equal sign as well. Then we add 50A minus 50A cancels, which it should. That's why we did it. 80 minus 50 is a 30B. And 6,800 minus 5,000 is 1,800. Then we divide by the 30 to find out that B is equal to 60 what? 60 liters. We denote that with a capital L. That's the proper notation. Now, once again, finish the problem though. I need to know how much of each type of solution. So I'm going to use 60 liters of solution B, and that's going to mean that my A, because A plus B is equal to 100, that means that A is going to equal 40 liters. So my answer would be that I would be using 40 liters of solution A and 60 liters of solution B to create a 100 liter solution that is 68% acid. Another common type of problem that they deal with linear systems are problems dealing with coins. In this particular example, it says on the table there are 20 coins. They're made up of quarters and dimes. Their total value is $3.05. How many of each kind of coin are there? Now, just because I love to do this because I am a gen ed instructor, I do want to point out one thing before we work on this problem. We have things in the English language called homonyms, words that sound the same but are spelled differently. And if they're spelled differently, they most likely have different definitions. Notice here that we're talking there, T-H-E-I-R. There is the possessive pronoun. Okay? It's talking about whose value? It's these guys, these quarters and dimes. It's theirs. They own it. It's their ownership. So that's why you use T-H-E-I-R. At the end, though, it says how many of each kind are there. There, in this case, is out there, that place. Okay? And then just so that we are well aware, there, which is our T-H-E-Y apostrophe R-E, is a contraction. It means two different words. They are. So it's they as in those two people over there, those two people over there, are something. Okay? So make sure if you are not sure, replace your word with they are to see if it's supposed to be there with the apostrophe. Or if it's a place, it's T-H-E-R-E. If it's owning or a possession, that's when you have the T-H-E-I-R. I would be remiss if I ended up not taking advantage of teaching about there, and there. Okay, now let's go back to our problem. All right, first of all, we have coins. Once again, identify our variables. What are we trying to find? Each kind of coin. Well, what kind of coins do we have? Oh, we have quarters and dimes. So I would say let Q equal the number of dimes. No, of quarters. And let D equal the number of dimes. So that's talking about our coins. Now wait a second, it told us how many total coins we have. We have 20 coins. So our first equation will be, we'll take the number of quarters, which is Q, add that to the number of dimes, which is D, and that'll give us our total number of coins, which is 20. So now we look at the next problem. The next equation gives us a value of $3.05. Okay, well once again we need to assign the value to our quarters and dimes, like we did with the children and the adults in the play problem. What's the value if I have 3 quarters, if the number of quarters I have is 3, how do I find that value? Well, we take that times the 25 cents that it's worth. Okay, well, I don't really like dealing with decimals, so I'm going to say that the quarter is worth 25 cents. So 25 cents times Q would give me the number of cents that I earned from my quarters. If I do cents there, I have to do cents for my dimes. Dimes are 10 cents. So I take 10 times the number of dimes I have. That's going to give me the value of cents that I got for my dimes, and that's going to equal the total value. Okay, in this case, this gives me a value. Taking the 25 times Q gives me a number, cents, a value of those coins. Added to this is going to give me a value, but they gave us dollars. I just used everything in cents, so I have to convert the $3.05 into pennies, which just moves your decimal point over 2 spots to the right, so it's the same as 305 cents. And now I have my 2 equations. I always like to eliminate my smaller variable if I can, so that I don't have to deal with negatives. So I am going to get rid of my d's. I have 10d over here, so I need negative 10d to add to it. To make this negative 10, we're going to multiply this entire equation by negative 10. Once again, I'm just going to rewrite that underneath. That's going to give me negative 10q minus 10d is equal to negative 200. Okay. Add them together, 25q and a negative 10q, same thing as 25 minus 10, gives me 15q. 10d minus 10d cancels out as it should, equals, we drop that down, 305 minus 200 is 105. Then to get Q by itself, we of course divide, and we end up with Q equaling 7. So that means that we have 7 quarters. Once again, read the directions, the question. We want each kind. So if there are 7 quarters, we had 20 total coins. That means 20 minus 7, or the number of dimes, is 13. 13 dimes and 7 quarters. This is how you might set up a coins problem. Now, sometimes they're not always worded like that. Say they don't always give you the total number of coins. Maybe they compare the number of dimes to the number of quarters. But this gives you an idea of how to set up the values on it. Anything else, you may want to read some of your example problems in the textbook to get an idea of how to set it up if they don't tell you the number of total coins, and instead they compare the number of quarters to the number of dimes. That might be beneficial. Read the book. Another tricky type of question deals with age, because we forget about adding ages or subtracting ages depending on how the years flow. So let's go through this example. It says David is twice as old as his daughter. In 4 years, David's age will be 3 times what his daughter's age was 6 years ago. How old are they now? Whew, that's a scary one. Once again, let's start off by defining our variables. What are they going to represent? So let's see, we're trying to find David's age and his daughter's age. Well, this is kind of bumming because David and daughter both start with D. I don't want to do that to myself and confuse myself. So I'm going to say let D equal David's age, and it's David the dad. So David's age. And then since the daughter is a girl, I'm going to say let G equal the girl's age. Okay, so what do we know about their ages? Well, right now, David is twice as old as his daughter. Now, we can start translating this almost verbatim. We still have David, which we don't know, so we can call that D. Is, in math land, usually translates to the equal sign. So we're going to say is, and then it says twice as old. Twice as old means that we're doing a doubling or taking 2 times. So it's 2 times the girl's age. Now, if you get a little bit confused on this as to where the 2 goes, stop and think about it. Who's older? Well, obviously the dad's older than the girl. So plug in numbers. If the girl was 5, 5 times 2. Yeah, okay, David would be 10. He'd be older, twice as much. Okay? If you had flipped it around and put the 2 by the D instead, suddenly you'd have the girl, the daughter, being older than the dad. Okay? So that's a good way of doing a check, just to say, does this make sense? Okay. All right, so now we go on. And it says, in 4 years, David's age. No, wait a second. David's age, the DU that we have, represents David's age now. Now. How old is he going to be in 4 years? Well, 4 years older. Okay, well, that would be represented by saying that he would be D, whatever his age is now, plus those 4 years. That's how old David's going to be in 4 years. Okay, so it says in 4 years, David's age will be is another way of saying is. It's just in the future tense. Will be, so that's equals 3 times, so we know that that's 3 times, means multiplication. But what are we multiplying? We're multiplying what his daughter's age was 6 years ago. Once again, we have the daughter's age now. How old was she 6 years before? Well, we don't know how old she is now, so it's harder to find out how old she was 6 years ago. But just like we did with the father, we can set that up and say, okay, no, that's going to be G minus 6. Now be careful though, because of what is this worded? It says David's age will be 3 times what his daughter's age was, which means we have to find out the daughter's age first. In order to do that first, only way that we can do subtraction before multiplication is if it's in parentheses. So G minus 6 represents the girl's age 6 years ago, and then whatever that is, we take it times 3, and that is David's age in 4 years from now. Whew. Let's clean that second one up. Use our good old distributive property. And then I would probably get my like terms together. I think I'll subtract 4. That wasn't very nice of me to put the 4 there. Should have moved it over a little. Alright, so now what do we have? Oh, we have craziness. Wait, I thought in all of our other problems we had to have our variables on the same side of the equal sign so that we could solve it. Well, wait a second. Let's think about this. We know that D is the same thing as 2 times G. We also know that D is the same thing as 3G minus 22. This is kind of a philosophy statement. If D equals this and D equals that, what can we say about this and that? If D is equal to this stuff, and at the same time D is equal to this other stuff, what can we say about the two piles of stuff? They have to equal each other. Essentially, this is your substitution method. D is equal to 2G. Wherever there is a D, I'm replacing it with 2G. Because logically, if D is equal to this stuff and D is equal to that, they have to be equal to each other. So let's see if I can pause. Alright, so setting them equal to each other gives me 2G is equal to 3G minus 22. Now here's an equation that we can solve. Get your variable terms on the same side. So I'm going to subtract 3G. 2 minus 3 is going to be a negative 1G, or negative G. Don't lose the negative in front of the 22. So negative G is going to be equal to a negative 22. Well, that just means that there's a negative 1 here, so I divide both sides by a negative 1, and I get G is equal to 22. So the girl's age is 22 right now, because that's what G stood for, was her age now. How can we find out her dad's age? Well, if you recall in that first equation, his age was twice hers. So David's age is 2 times 22, which is 44. So David is 44 years old, and the girl or the daughter is 22 right now. Feel free to go through and check. In 4 years, David would be 48. Is that 3 times her age 6 years ago? Well, if the girl or the daughter is 22 now, how old was she 6 years ago? 16. What's 3 times 16? Booyah! And it checks out. Slow yourself down and use a combination of the procedures that we're doing and common sense. We're going to end week 8 on linear systems with one final little thought that came from your book. Set a problem-solving tip. When solving problems, see if they are patterned or modeled after other problems that you have studied. Now, the problems that you're supposed to have studied are the other problems in the book, the examples. You're supposed to have gone through all of those and see where they come up with their stuff and do some of those practice problems that are in the margins in your book before you then proceed to practice some in each section. But oftentimes the problems in your homework have example problems that are very similar to them, or some other problems that are in your book. Use those resources to find out how to set up your problems so that they make sense and that you can be successful. Good luck.